Good evening, Robert Scribbler. It is June 19th, 2018. So for this segment, what I'm going to do is discuss with you a bit about the present state of atmospheric greenhouse gas accumulation. And the reason why we're going to look at this now is that May is a time when atmospheric CO2 levels peak due to the post-Northern Hemisphere buildup of carbon dioxide in the Earth's atmosphere due to loss of leaves during fall over the Northern Hemisphere during fall and winter. And this year, atmospheric CO2 levels peaked at 411 parts per million. And this is a very high number historically. If you look at the 1700 to present record, you'll find that during the period of initial coal burning, due to the start of the Industrial Revolution, atmospheric CO2 levels, which started out around 275 parts per million, steadily increased through 1900 to just below 300 parts per million and to around 310 parts per million by 1950. And in the subsequent period of very rapidly increasing fossil fuel burning, atmospheric CO2 levels rocketed from the mid-1950s at around 310 parts per million to around the 410 part per million level that we see today. Now, during May, atmospheric CO2 levels peaked at around 411 parts per million, and next year, on the present trend, we can expect an annual peak at the Mauna Loa Observatory at around 413 parts per million. Now, historically, these are extraordinarily high levels, and the further you go back into deep history, the more you recognize how extraordinary these atmospheric CO2 levels are. And so, for example, the average atmospheric CO2 levels during the Ice Age period has been around 220 parts per million, and we're nearly double that today. But the further you go back, it takes us quite a long time to find a period in which atmospheric CO2 levels were as high as they are today. In fact, you have to go back to the Middle Miocene period of about 15 to 17 million years ago to find a time when atmospheric CO2 levels were consistently above 410 parts per million. And we are entering that time now. Because fossil fuel burning is continuing, it is unlikely that we will see the 410 parts per million number again unless we somehow learn how to pull down carbon dioxide from the atmosphere, in addition to fully transitioning our energy infrastructure to renewable energy such as wind, solar, and electrical vehicles. Now, carbon dioxide is the primary contributor to human-forced climate change and global warming, but it isn't the only heat-trapping gas in the Earth's atmosphere. And so NOAA has provided a greenhouse gas index, which gives us an idea of what the total greenhouse gas forcing on a comparative CO2 basis is. And it includes atmospheric greenhouse gases such as nitrous oxide, methane, and various chlorofluorocarbons and other chemical hydrocarbon-based substances, which also trap heat. And what NOAA has found is that the carbon dioxide equivalent presently is 493 parts per million. And that includes CO2, which is the primary contributor to radiative forcing at the top of the Earth's atmosphere, but that has a not insubstantial contribution from these other gases. So 493 parts per million is quite a bit more than 411 or 410 parts per million. And And if we exceed 500 parts per million, we're starting to look at time periods in excess of 20 to 30 million years if we're to try and find an equivalent time period. Now, if you look at the middle Miocene of 15 to 17 million years ago, global temperatures range from about 3 to 4 degrees Celsius above normal, and that would correlate roughly with atmospheric greenhouse gases in the range of 410 to up to 500 parts per million. Now, the 493 parts per million number represents warming that is potentially a bit higher if you compare it with past climates, possibly as high as 4.7 or 4.8 degrees Celsius total warming long term. Now, on 1 century timescales, we can have those numbers. So the 411 parts per million number roughly correlates to around 1.5 to 2 degrees Celsius warming by the end of this century. And the 493 parts per million number roughly correlates to around 2.3 degrees Celsius warming by the end of this century. And that provides us with a decent range of how much warming we could expect under current atmospheric forcing, even if it were just to remain stable. Now, unfortunately, what we are seeing is that atmospheric carbon dioxide and other greenhouse gas emissions due to fossil fuel burning and other activities is still rather high. And in fact, during the early 2000s, increased very rapidly, but over recent years has hit a bit of a plateau. And the reason why we have hit a plateau recently is because coal use is slowing down and starting to decline in a number of regions. We have wind and solar energy sources that are now competitive with both coal and natural gas for electricity production, and electrical vehicles are starting to compete with fossil fuel burning vehicles for gasoline use. And so what we have right now is the opportunity to start to reduce annual global carbon emissions in the form of carbon dioxide and other greenhouse gases if we continue to pursue an aggressive transition to renewable energy, and if we support policies that speed that transition. Now, from an economic standpoint, renewables are already, in many cases, stronger than coal and natural gas and oil. And simply deploying these new renewable energy sources will result in a reduction in annual global carbon emissions. And the more rapidly we deploy those, the more rapidly we will reduce those carbon emissions. And there's a potential, if we are aggressive as a global society, to reduce net annual carbon emissions to zero in the 2040s to 2050s timeframe. And we should absolutely work to achieve that goal, especially considering how far behind the 8 ball we are when it comes to global temperature increases. Now, if we do that, we could be looking at around a 550 atmospheric CO2 equivalent forcing in the global atmosphere at that time, which would be difficult enough to deal with. But if we continue to burn fossil fuels, those numbers will be much higher.